Yeah, let's start chapter 8. This works with identification of processes. I want to show you 6 different methods. There are thousands of methods available in literature. Scientists working since 50 years on methods to identify processes, because this is necessary for control system theory, because without any knowledge about the process you have no chance to design a fitting controller. So the design needs information about the process. So there are many methods. The MATLAB toolbox, the identification toolbox, contains hundreds of methods, complicated, simple. What I want to show you is starting with very simple method with 8.1, where we make an identification with, we call this characteristic values. Then we go over to more and more complicated methods, which needs some tools, some numerical source code to identify the process. We will end finally with 8.6 with a for me a modern solution, rather old but still modern, which is called online identification, where during the control loop is running, the identification is activated in each step. So if the model changes during control, this online identification detects this change and can adapt automatically the controller. So this is a rather nice method. All methods just with a goal, with the objective to have a model, to have information so that the design of a controller can work. No other purpose is useful, is necessary. Okay, let's start with a principal idea of identification and a method how to test the identification method. Let's think about the idea of testing of identification method. One test possibility is the following. I have a model A, a numerical invented model A. Take any model A, then create responses. For example, step response of model A, or any other type, impulse response, a response on several sinusoidal functions to get the frequency response. Create responses and then identify a model. Identify model B. So there, maybe you have the numbers of model A, and identified model has also numbers. Then compare numbers. If numbers fit and the numbers are the same between A and B, then your identification is good. If numbers are different, okay, then you don't know if the identification is good or the model B is good. Compare numbers. But sometimes in spite of big differences of numbers, model B could be good, acceptable. Okay. So the comparison of numbers also doesn't work if the type of the model A and type of model B are different. Say we will see in a numerical method where we can identify say 10 PT1 system, we create responses and identify a 2 PT1 model B. Then the numbers of A and B fits to different models, and then you can't compare. Compared numbers is not possible if model is different. Comparison of numbers doesn't work if model type A is different to model B. Then you cannot compare numbers. How can we test? In this case, how can we test the quality of your identified model B? This test works just with a closed loop system, because the identification is only used to design a controller, which then I can run with model A. I think this is the hardware, that is your real industrial process. This is a mathematical model. Design a controller with model B and run with your industrial process. That is real life. The test should work in a closed loop system. So what we can do is the following. We have our model A, same steps like before. Model A. We of course create responses. Of course, then identify a model B. Then what we do is we design a controller with model B. On the base of model B, design controller. Say, I call this controller B. And then test, take a loop, build up a loop, take your controller B, which you have designed with your identified model, put it together with model A, and then close the loop with negative feedback. Apply a test signal, mostly a unit step function, measure the reference step response, and then look for this reference step response if this is acceptable. So then you have a real test of your identification model. Doesn't matter which type, which numbers. This model, which is used for designing the controller B, this controller should work together with your original model A, your industrial process, and should work with a good behavior. So the good test of a closed loop system is a reference step response. Quick change of desired value gives the quick response of your controlled output. This is a best test, and we will do this in several times in our next methods. Sometimes the comparison of numbers is sufficient. If you have a mathematical model A has an identification, and to get an identified model B, which is in type and in numbers exactly equal model A, then of course your identification is the best. But sometimes this doesn't work. And don't forget the industrial process. If model A is an industrial process, you have noise, you have nonlinearities, and the same identification method you use here could deliver a model which doesn't fit, and you don't know the numbers of model A because this is a physical process. You have to get a model B and you have no idea if this works together with model A, then only this test method works. because here you can test really your final resulting controller together with your industrial process, and only this is that what you want to have in industrial processes, a good closed loop system with good reference step response, or of course disturbance step response. Yeah, both signals must fit to your that is a disturbance step response. If you have a disturbance here, a summing point with disturbance signal here, then you get the disturbance step response. Yeah, both in your application, both things should be optimized depending on your process. Okay, so far the introduction words for your identification methods. So we can start with the first chapter 8.1, identification, short ID, using characteristic values. This is a method which can sometimes be done manually without the help of the computer, and this is adapted to the typical model types we can find in industrial processes, adapted to typical processes, typical process types, and the typical process types is PT1, that is a pure single PT1 system which very seldom can be found. Then was IT1, that is an integrating process with one delay. Then a PT2 with oscillation possibilities, or with typical process is a chain of a number of PT1s, and the number of PT1s could be 2 or 3 or 5 or 10 or 1,000, doesn't matter. If you have a chain of PT1s, I give you in chapter 8.1 some ideas to identify a good model for controller design. So typical for 8.1 is use step response. Yeah, step response. If you cannot measure the step response, then 8.1 cannot be used. Yeah, the 8.1 chapter needs a measured step response, and it needs also good information which kind of type you have. If you don't know the type of your process, and the type doesn't fit to one of these 4 typical types, you cannot use this method. So let's start with 8.1. Say this is A, B, C, D. 8.1a. We look for a PT1 step response, and I think that is a repetition, because everybody of you, I think, knows how to identify a PT1 system with a measured step, PT1 step response. Let's look for this step response. I give you a very quick comment to your result. We can work with the unit step response, but I want to look directly for a measured step response, U2 of t over t. If what happens if you have a system, we want to find a model, say Fm of p. Best is we know the coefficients of transfer function. We apply a step function at input with a given amplitude. This must not be 1. Should not be 1. And then this is the step response, which we can call U0 times sigma h of t. Now this is the linear, we assume linear behavior if we have the unit step response h and the input step amplitude is not 1 but u sub o, then the output amplitude also is multiplied with the same factor. So this is u2, this is u1. Now we can say u1 is u0 times sigma of t. That are the names I use in control system 1. Okay, let's look for the typical PT1 step response. We assume a non-delayed, offset cleaned step response. If there is an offset signal on this curve, then of course you have to clean this measured signal by the offset value. This is the final value of output. This is the time constant of the PT1 process, and sorry, that is, yeah. And we have the typical exponential form of step response. Assume you have measured the red curve. We want to identify our model fm of p, and if we see this curve, we at once can say this is a PT1 system, and then we can look into our table of different kinds of system, and then we can very easily find that the typical PT1 transfer function is k divided by 1 plus pt, and the identification should give us a method to calculate k and t. If we know k and t, we know all of the system. It's two expressions very often used in modeling. This is an information. The red curve is an information which carries normally many points as the coordinates of points. So in a scope, in a digital scope, you should know that the signal then is sampled, and the values, the sampled values, are stored in a table, and you can extract these sampled values in a table. So this may be hundreds or thousands of points with coordinates t value and u2 value. This information has a name. It's called a non-parametric information. Non-parametric information. Here on this side, on the right side, this information is also an information about the kind of the process, but you see there we have two parameters, a parameter k and a parameter t. So this name is a parametric information. Note that if I know the transfer function of a model, I know much more compared with the step response of a model. Yeah? A step response is a response of a special input signal, a step function. This is the transfer function, which is a ratio of any input signal, any output signal divided to any input signal. So this contains much more information about the process than this, in spite of the fact that the data amount of the left side is much larger than the data amount of the right side. Look for the data amount. Say 1000 points x epsilon. So say x and epsilon are floating point numbers with 4 bytes. We have 8 bytes, so this is 8 kilobyte information. The parametric information contains two values, 2 parameters. Uh, 8 byte if one parameter is stored as a floating point value with 4 bytes. Then we have a data amount of 8 byte compared with 8 kilobytes, so 1000 times more data amount but less information. Here you can see the data amount is not relevant for our information. The information could be less in spite of the fact that the data amount could be large. Here's the data amount small, but the information part of these both parameters is very high. So that's the idea of identification, to take in non-parametric information created by measurement to make an information increase, data reduction, to get a frequency model, a transfer function, which is much more useful for our identification, for our controller design or any use than a non-parametric information. Okay, so this is a good way to show that data amount is not the same as information amount. We want to have information and not data. Okay, back to the real purpose of our step response. I give you 3 ideas to get the time constant, 1 idea to get the k. To get k is simple. K is the final value of your signal divided by input voltage. K is, say here, final value. K is final value of step response, but the K is the DC gain of your model, and if your input signal has an amplitude U sub O, then you have to divide this by U sub O, and you know I have made a mistake. The final value here is of course K times U sub O. K is the DC gain of your process, and you get the K by dividing the final value by your input voltage of your step function. So consequence, you have to measure long enough to get final value. If you stop your measurement, say here, you cannot extrapolate the final value. So you have to wait long enough, say up to here or here, then you can say, okay, I can extrapolate the final value and get a good information of K. So this method needs a measurement time which is longer than your expected time constant. Measurement time should be around 3 to 5 times of your unknown but identified time constant of the process. Okay, black color. How can we get T? To get T, there are 3 methods known in literature. Maybe there are more methods, but 3 typical methods I want to show you. The first is say Roman 1 is draw starting tangent. Draw starting tangent, I have indicated this in my drawing, that is the dotted line. And if you have the starting tangent and you have the final value, the cross point of starting tangent with final value, the cross point defines cross point defines t. Now this cross point here. That is in the case A, first method. The second method is also well known. Look for the 0.36% final value point. That means the exponential function crosses the time constant t value if we have 0.63 times k times u sub o. If we have reached the 63% value of the final value. So yeah, if you know the final value, go back to the 63% value, then this time is your searched time constant of the process. Then there is a third method. Use we call this 10 to 90% time. What is this? This is called the rise time. Rise time calculation in scopes, digital scopes. Very often this is a mathematical algorithm behind your measurement. So the scope throws out the rise time, and the rise time is measured. I just draw the curve again, the step response like this. You need to find a value again, k times u sub o, and what some algorithms, some scopes offer is, here you have 0.1 k u sub o, and here you have 0.9 k times u sub o. So the 90% value, here the 10% value, and say in green, this time and this time, the difference of both times is the rise time, say tr, rise time tr. So, and the rise time tr also is proportional to the time constant. You can now calculate, the with the mathematical h of t, which is k times 1 minus e to the power of minus t divided by time constant, the well-known exponential equation of the unit step response, of course multiplied with u sub o. You can then calculate, I don't want to do this here in detail, but with some steps you can solve this equation for the two cases. If this is a t10 time, you have 10%. If this is a t90 time, you have 90% of the output. Say 0. I write it on 0.9 times u sub o times k. That is a 90% value, is u sub o k 1 minus e to the power of minus 1090 over t. With the second equation, 1 minus e to the power of minus t10 over t. Then we have two equations with two unknowns. K is the unknown, t is the unknown. You can solve this. Solve. And then you get the solution. T is, I have to look in my paper. Oh no. Yeah, here you can see the result. I have looked in my paper. The time constant t can be calculated by the difference of both measured times divided by a natural logarithmic function of 9. If you replace the difference with your rise time divided by L9, you get the result. The time constant of your measured PT1 system is 0.4551 times this rise time. This is a method to get K and T without knowing final value, and I think this comes now in the next video. And final fourth method, if you don't want to wait long enough to get the final value. Yeah. Okay, this comes with the next video.